Welcome to part 2 of the vectors lecture. In this part we'll take a look at two ways of multiplying vectors together, the dot product and the cross product. Both have their uses in maths and physics and will be very useful to us in understanding and modelling vehicles and collisions. There are two types of vector product, the dot product, which produces a scalar result, hence its alternative name of scalar product, and the cross or vector product, which produces another vector as a result. We'll deal first with the scalar product. The dot or scalar product of two vectors produces as a result a scalar quantity, in other words just a number. For two vectors A and B, A dot B is the magnitude of vector A multiplied by the scalar component of vector B parallel to vector A. That's all very well, but what does this actually mean? Let us have a look at what the definition of the dot product means geometrically with two arbitrary vectors A and B. The magnitude of A is easy to determine, and we already know how to do that. We can now determine the scalar component of B parallel to A by defining a right-angled triangle as shown. Another way of describing the scalar component of B parallel to A is as the projection of vector B onto A. We know the length of vector B, so the projection of vector B onto A is given by trig as the magnitude of B multiplied by the cosine of the angle between the two vectors, which I've called angle theta. Thus the product A dot B can be defined as the magnitude of A multiplied by the magnitude of B multiplied by the cosine of the angle between the two. Now that we have a definition for A dot B, we can look at a specific example. Let's suppose that vector A is 13 units long and that vector B is 10 units long, and that the system is arranged such that the angle between A and B is 50 degrees. Then A dot B can be calculated as 13 times 10 times cos 50, which is approximately 83.6. This is easy enough to do, but it doesn't really tell us anything useful. To put the dot product to practical use, we need a little more work first. Think about what happens to the projection of B onto A if the angle between the two vectors is 90 degrees. In such cases, the projection must be zero. This is shown by considering the definition of the dot product. The cosine of 90 degrees is zero, so that for a 90-degree angle between the vectors, the product A dot B must also be zero. Now the dot product will be zero if either A or B is of zero length too. But if A and B do have size, then if A dot B is zero, this means that the two vectors must be perpendicular. This is a very helpful test for determining whether two non-zero vectors are in fact perpendicular. Consider now the unit vectors I, j and k as in the definition of a general vector A. Since I, j and k form a right-handed orthogonal system, in other words they are all perpendicular to each other, then I dot j will be 0, as too will be I dot k and j dot k. We now need to consider what happens to the dot product of parallel vectors. With parallel vectors, the angle between the two must be 0. Since the cosine of 0 is 1, then the dot product of A and B will simply be the product of their respective magnitudes. In particular, this means that the dot product of a vector with itself, A dot A, will be the magnitude of A squared. This too has consequences for our Cartesian unit vectors, since I dot I will be 1, J dot J will be 1, and K dot K will be 1. Now that we know how the dot product is applied to the unit vectors I, j and k, we can see what happens if we take the dot product of each of the unit vectors with a general vector A equal to A1i plus A2j plus A3k. The product A dot I can be found as shown and then expanded as follows. Since we now know that I dot I is 1 and that j dot I and k dot I are both 0, the only component left when we find the product A dot I is A1. A similar line of reasoning leads to the conclusions that A.j is A2 and that A.k is A3. Now we can take a second general vector, vector b. As with vector A, we find that b.i is b1, b.j is b2, and b.k is b3. This now allows us to find the result of A.b, which ends up being A1b1 plus A2b2 plus A3b3. Now that we can find the product of two vectors in Cartesian component form, we can put this information to some practical use. The dot product turns out to be a very convenient and practical way of finding the angle between any two vectors. In this example, we have two vectors, A equal to 5i plus 3j and B equal to 4i minus j. From our earlier definition, we know that A dot B is equal to the product of the magnitude of these two vectors and the cosine of the angle between them. Rearranging this equation for cosine theta produces the quotient A dot B over the product of the magnitudes of A and B. We'll need the magnitudes to perform this sum, so we'll find them first as root 34 for A and root 17 for vector B. We can now find the product A dot B using the method we developed in the previous slide. Working this through, we find that the product is equal to 17. This means that for this example, the cosine of the angle between the vectors is given by the expression 17 over root 34 times root 17. This turns out to simplify to 1 over root 2, which is approximately equal to 0.707. The inverse cosine of this number is 45 degrees, or pi over 4 radians if you prefer. We now move on to the cross product. We'll start off by defining the magnitude of the product. The magnitude of the cross product of two vectors A and B is defined as the magnitude of A multiplied by the component of B perpendicular to vector A. This is very similar to the definition of the dot product we explored earlier, with the substitution of the word parallel in the dot product with the word perpendicular in the cross product. A little geometry leads to the conclusion that the magnitude of A cross B is the product of the magnitudes of each of the vectors and the sine of the angle between them. However, this is not all. The cross product is also known as the vector product, which really emphasizes the fact that the cross product is itself a vector. Although we have already defined the magnitude of the cross product, that is all we've defined. The cross product is actually defined as the magnitude we defined earlier multiplied by a unit vector c. This unit vector c is defined so that it is perpendicular to both A and B. Before moving on any further, I need to talk a little bit more about this unit vector c. The unit vector c has a direction which can be determined using the right-hand rule, or at least a variation on it. Using a right hand, if you align your thumb with vector A and your first finger with vector B, then the direction in which vector c points is given by your second finger. Try it with this example. You'll find that your second finger points away from you, so that the sense or direction of vector c is into the screen. This means that A cross B does not equal B cross A. In fact, by swapping the two vectors A and B, we find that A cross B is equal to minus B cross A. The vector c points in the opposite direction. We can use this information to see what happens to the cross product when two vectors are parallel. When two vectors are parallel, the angle between them is 0, and since the sine of 0 is 0, the cross product will also be 0. In a similar way as dot product can be used to test if vectors are perpendicular, a 0 result for the cross product of two non-zero vectors means the two vectors are parallel. Taking the cross product of a vector with itself leads to the conclusion that A cross A is also 0. In turn, this means that for the Cartesian unit vectors I, j and k, the cross products I cross I, j cross j and k cross k are all 0. Let's consider now what the cross product for orthogonal or perpendicular vectors might be. For perpendicular vectors, the angle between them is 90 degrees. The sine of 90 degrees is 1, so that the result of A cross B, where the two vectors are perpendicular, is a vector with a magnitude equal to the product of the magnitude of the two individual vectors in a direction 90 degrees to both A and B. This means that for the unit vectors I, j and k, which have a magnitude of 1 by definition, the product I cross j is k, j cross k is I, and k cross I is j. Also, since A cross B is equal to minus B cross A, this means that j cross I will be minus k cross j will be minus I, and I cross k will be minus j. All this information allows us to work out the cross product of two general vectors A and B expressed in Cartesian component form. A cross B can be expanded and rearranged with a little work to give A cross B is equal to A2B3 minus A3B2 I plus A3B1 minus A1B3J plus A1B2 minus A2B1 K. Note that because the cross product always produces a result perpendicular to both the original vectors, the cross product of 2D vectors in the xy plane will always produce a vector exclusively in the z or k direction. So for 2D vectors in the xy plane, the cross product can be simplified to a1b2 minus a2b1k. Here's a simple example of two vectors in the xy plane. We'll use the same data as previously, with a equal to 5i plus 3j and b equal to 4i minus j. Since we know that these are both vectors in the xy plane, we can use the simplified equation to find the cross product. So a cross b is equal to 5 times minus 1 minus 3 times 4k, which is all equal to minus 17k. Note that the minus sign indicates that the resultant vector is in the negative k direction. Using the right-handed orthogonal system, positive k is upwards out of the screen, so a negative k means a vector which is pointed downwards into the screen. This is all very well, but the question has to be asked, does any of this have a practical use? The answer is very definitely yes, as this short list shows. And that's just some of the uses in mechanics. Both vector products have uses in other topics in physics, such as electromagnetism, optics, and general relativity. This is the end of part 2 of the vectors lecture. In this lecture we explored the two vector products, the dot product and the vector product, and discovered ways of using them with Cartesian unit vectors as well as some practical applications. Thank you for watching.